So when we are dealing with the diagonalization, we are given a matrix A that we want to diagonalize. Then we subtract A minus lambda I. So we subtract the lambda only for the diagonal terms. Then we write down the determinant of the matrix A minus lambda I. From the determinant, we get the polynomial of degree n in lambda, the roots of this. So this is the polynomial. So this is poly, and this is roots. And x will be the eigenvectors. Then from x, we can determine what is the matrix P, which is a matrix which allows the conversion from one basis to the other. Okay. So now, in principle, this is what happens with when we find the eigenvalues and eigenvectors. Now we are going to move to a new chapter, which is application of diagonalization. How can we make use of these? Now, of the diagonalization principles. So now, let's think for a moment that here we have a standard basis. Here we have the matrix A. Once we find a new basis, which is composed of the eigenvectors of A, now here we get a diagonal matrix D, and this is the matrix A. And this is the base. We have also the P, which we can find from here. This is the matrix which allows the transformation from this domain to the other. And then the relevant equations, they are the following. So let's assume here we have a vector x, and here we have a vector u. Now it is obvious that we need to apply this operator onto u to get x. Okay, so here we say that x, which is in the standard basis, is equal to the matrix P times vector u. Okay, and now today we are going to see that we can generalize this problem a little further, because we can have that u is a function of time, and this is still a vector, and at the same time we can also have the representative of the ut also in the standard basis. So we could see this expression again, xt. This can be written as the matrix P times ut. The only thing is that we have to figure out how we can generate the ut. Let's start. So this is how the vectors are transformed from one basis to the other. Then we have also the transformation of the matrices. Now, to diagonalize a matrix, we know that any matrix A, we multiply it with P inverse and then with P, and we find the matrix D. So what we can do here is that we can multiply both sides of the equation with P, and here we get the following. So PD is equal to PP inverse AP. So we just multiply from the right side, from the left side, both equations like this. And P times P inverse, this is the identity matrix. So we get the PD is equal to AP. Okay? And then what we can do next is that we can multiply from both sides of the equation. From the right side, we multiply with P inverse. And here we have another identity matrix, and we find that P inverse, this is equal to matrix A. So these two relations, these are essential for us. This can be intuitive how we find this, but so we could have written this right away, that A is equal to P inverse. And then the use of this relationship, it is very important, especially when you have expressions which might be like polynomials in matrix A. So if we have matrix A squared can be written as A times A, and here we have P inverse times P inverse. Okay. So if we have this multiplication, the first calculation that we do, we find what is P inverse times P. Okay, and this is equal to the identity matrix. So this is equal to, we can write this, well, let's continue this here. This is equal to P, B, D, P inverse. And then if we multiply these two matrices, we get here P, D squared, P inverse, okay? So it looks like it is, well, we can do it like this. So we can say that if here we have the D squared, on the other side, we have also A squared. But to transfer from one to the other, this is the structure that we use. Similarly, A to the power 3, this is equal to P D cubed times P inverse, okay? So this is relationship, it still holds. And here, in any case, if we have A to the power n, this will be equal to P D to the power n, P inverse. Now, we need these calculations because we know that whenever we multiply two matrices, if we have matrix A, let this be a square matrix n by n times matrix B, which is also n by n. So this is going to be equal to the matrix C n by n. Now, then the multiplication here, we denote this as follows: Aik Bkj. This is equal to Cij. Okay? So any element in C which can be found in row I and column J is equal to row I of A times the column J of B. And what is changing here is that this is equivalent to the summation k from 1 to n of Aik Bkj, keeping I and k fixed. So now, if we have so it looks like for each element, a single element in the matrix C, how many calculations do we need to do in order to find a single element of Cij? So if we look at this expression, how many calculations do we have here? This is equal to
n calculation. It is a summation from 1 to n.
N calculation. What are these calculations? Are they additions or multiplications?
We multiply the values from A and B and then add the results together.
Yes, but let's have a look here. So
it's like similar to the inner product. If
it is like inner product. But how many multiplications? And
so n plus 1 multiplications and n additions.
N multiplications and n minus 1 additions.
The last version, it seems more correct. So
yes, because there are n terms.
Yes, so we have n multiplications and n minus 1 additions. So in total, we have n plus n minus 1. So these are the number of calculations for each Cij. Now, how many elements does the matrix N have? Sorry, does the matrix C have?
N times n.
N squared.
N squared.
The whole C matrix, it has n squared elements. So if it has n squared elements, then the total number of calculations, so we say the number of calculations, this is, what is it? This is n squared times 2n minus 1. Okay, 2n minus 1, because this number, this is 2n minus 1. So in total, we get a number which is 2n to the power 3 minus n squared. So it looks like this is a relatively high number. So how much time what you can calculate here is if we have a matrix which is C, which is 1000 by 1000. So what is this matrix? 1000 by 1000. This will be the image that you can take with your camera of your cell phone. Okay, cell phones are in this year they are in the order of 10 to 20 megapixels, and this is something. This is the number of entries into an array of an image. So you have 1000 rows, 1000 columns, and 1000 rows. So in this case, if you need to multiply all of these, how much time does it take? It looks like if we want to multiply two matrices, which can be two images, we multiply them, and it takes 2n cubed minus n squared. This is 2 times 10 to the power 3, this is 1000, to the power 3, minus 10 to the power 3 all squared, okay? So the total number, this is equal to 10 to the power 3, to the power 3, what is it equal to?
10 to the power of 9.
10 to the power 9, minus 10 to the power 6. What is 10 to the power 9 minus 10 to the power 6? This is approximately 10 to the power 9, okay? Approximately. You can keep it like this. This is more correct. But this is approximately equal to this. You can multiply it also with 2. So, sorry. 10 to the power 9 times 2. I forgot the 2. Okay. So, how long does it take for a computer to do this much calculations? So, you have the number of calculations.
Less than a second.
Say it again.
Less than a second.
What speed are you considering?
We need to know the CPU speed.
Usually image processing is done with 2 for loops, with one loop going over each 1000 elements. So it's the complexity is O(n) square, and it takes like a million. I'm not sure. It depends on the
Let's say
frequency of the processor.
let's consider the frequency is 1 gigahertz. So it might take 2 seconds, okay? So if we generate two random matrices, we multiply them, and we want to find the time, it might be something in the order of 2 seconds. Fine. Let's keep this was just small calculations of how we can count the number of operations in a specific case, as we did in here. But imagine for a moment, we can have a matrix which is a to the power n, and this is equal to p, d to the power n, and p inverse. If we have d, which can be numbers like this, 3, 0, 0, 0, minus 1, 0, and 0, 0, 1. How many, if we have here, let's say, d cubed, this will simply be 3 to the power 3, 0, 0, 0, minus 1 to the power 3, 0, 0, 0, just 1. Okay, so the number of calculations is really limited to a much smaller number if we have transformed the whole system into a new basis. Because matrix A, it can be done. So the powers of matrix A can be simply calculated by just calculating the powers of matrix D. So this is one of the useful or important improvements that we can do if we use the matrix, the diagonalized version of the matrix. Now, let's take this out for a moment, and also this part. And now, let's assume a system that is evolving in time, okay? A system that evolves in time, we can provide several examples where an possibly acceptable example is one where let's say the number of populations of animals. If you have animals which multiply in nature, assuming that we have no predators, okay? So let's assume you have rabbits but in the mountain there are only rabbits, there are no foxes, and there are no wolves, which means that we don't have predators. So they just die naturally. The number of rabbits might increase very fast, and this one might be represented as follows. So we can have xt plus 1. This can be equal to a constant a times xt. So apparently this is how they might multiply. And then, so for example, if a, let's assume for a moment that a is a number which is equal to 2. That's good. And then we can also get the following. If we go back, we can say that x1, this is equal to a times x0. Now let's assume that we have x0 is the number of rabbits that is initially. Let this number be 3. And then we want to see how fast do the rabbits increase after, let's say, 4 generations. And then if we have x1 is equal to ax0, x2 would be ax1. So this would be ax1, it's ax0, right? So this is, we can write that this is equal to a squared x0. Then similarly, we might get that x4, after 4 generations, this would be equal to a to the power 4 times x0. And similarly, we can say that xt, this is equal to a to the power t times x0. So this is how numbers might generate, or might evolve. But for a moment, let's assume that, let's try to find what is x4. x4, if you assume that a is equal to 2, we get 2 to the power 4 times 3. So we get a number of around, what is this? 4 times 4, 16, 48.
48.
48, thanks for the confirmation. So it looks like this is how we can find how the numbers of the rabbits is increasing after 4 generations, or after 4 time scales. Assume the time scale can be something like a reasonable number. And I asked my son one day, my son asked me, he said me, how long is a generation? I said, I don't know, you find it. He said, how should I find it? I said, subtract my age, your age from my age, and you can calculate the generation. So, now, this problem, so that would be the time frame of a specific generations. Now, here we are just dealing with numbers. But this does not have to be a number. This can be a vector, where we can have that xt is equal to a matrix A times xt minus 1, okay? So this is the fundamental relationships between these any two vectors. Then, sorry, this becomes like a little mess. This is t minus 1. Then, using similar arguments, we can say that any vector after a certain number of time frames or steps, this can be written as a to the power t, where a is the matrix, times x0, where x0 it is the initial number at the initial very first stage. So, and regarding this problem, we can give an example. And in this example, let's assume that we have x t plus 1. This is equal to 7 xt minus 15 yt. So apparently, the way to consider this one might be the following. So let x be the number of rabbits, and 15 is the number of foxes. So more foxes we have, they're going to eat some rabbits. So the number of rabbits later on is going to be 7 times. So let's assume that they are multiplying with a factor, which ends up to be 7. 7 times xt minus 15 times yt. So these two we might consider like the population of two different mammals that compete with respect to each other. Then, if this is the expression of xp, then yt plus 1, this can be another animal, which is, or bacteria, 2xp minus 4yt. Actually, nowadays, during the times of pandemic that is keeping the classes online, these examples, they are the solutions of the how particles or how bacteria or how microbes, how they generate. The use of linear algebra or the use of matrices is it supports a lot all the calculations that we conduct. Now, these are difference equations. This is not the best thing that we can do, but one better approach, which still uses linear algebra, is the solution of differential equations when we have two or more bacteria or two or more viruses that are competing with each other. Now, here, let's assume that we have different viruses, that the one be X, the other one is Y, and they are related with respect to each other based on the equation given here. And let's assume that initially, at the initial stage, somewhere in a market around the world, we are given this much of x0 is 1 and y0 is equal to 1. Now, this system that we see that this system is a coupled one. Okay, so this is an important keyword that I want you to take to remember. So this system is coupled because x depends on x and y depends on y and x. Now, this is coupled as long as the system is described by a matrix A. And what we want to do this. We want to decouple the system, or we want to represent this relationship using a matrix D, which is diagonalized. Now, how can we do it? Let's try to follow the following pattern. So we have xt plus 1, yt plus 1. This is a vector, which is a vector 2 by 1. And this is equal to a matrix which is 7, 2, minus 15, minus 4. Here we have a matrix which is 2 by 2 times the vector xt and the yt. So this is, wait a second, no, this is correct. This is 2 by 1. Okay, so this is the general picture that we're going to work with. And let's take this out for a moment. So here we have 7 minus 15 to minus 4. This is a matrix which is in the standard basis. And now we want to represent this whole problem using a new domain. What we need to do here is actually the procedure that I just erased. I should have kept this a little longer. And to solve this one, all we need is that actually before we diagonalize it, let's give the formal definition, which is equal to so here we have the matrix A, and after here to find the matrix A, we need to find the matrix D, which is the diagonalized version. And the matrix D, it's composed of, let me see here. I remember we solved this problem before. It has...
Yes, the eigenvalues are 1 is 2 and 1 is 1, 1 and 2.
Okay, what, do you remember the eigenvectors?
Yes, one is 5, 2, and the other one is 3, 1.
Okay, thank you for giving these numbers. And what is important is that does the 5, 2 correspond to eigenvalue 1? Is the 5, 2 the eigenvector of eigenvalue 1? Because this matters, because it depends. If we put 1 here, we should put the eigenvector of 1 right here. So let's check this. Let's check the following. This is equal to 7, 2. Well, we can try to find this one. let's subtract 1. So here we have 7. So we have to do the following. This is 6, 2, minus 15, minus 5. So this is times 8.
Sorry to interrupt. It's 5237, not 21.
5, 2, and then
37.
3, 7 here.
Yes.
Okay. Let's see if we get those numbers. So if we have this is 6 minus 15, because this is equal to matrix A minus lambda, which is 1, times the identity matrix, okay? Which means that we have to subtract 1 from the diagonal terms. So 7 minus 1 is 6, minus 4 minus 1 is minus 5, so this is what we get. And then we have here 6A is equal to 15B, which means that A is equal to, divided, so we get 2A, this is equal to 5B, so this is 5, 2, that is correct, this is 5, 2. And then let's construct another matrix, which is A minus 2 times I. For a matrix which is A minus 2 times I, we get the following. 7 minus 2 is equal to 5. This is minus 15, and this is 2. And we have minus 4 minus 2. This is minus 6. And if this is the case, then we have times AB. This is equal to 0, 0. Then we have the equation, which is going to be 5A. This is equal to 15B. So A is equal to 3B, which means that this can be 3, 1. Then. If the eigenvalue is 2, this will be 3, 1. So this 2, I'm doing this in black, this eigenvalue of 2 corresponds to an eigenvector 3, 1. Okay? So if this is P, then the next step is that we need to calculate what is P inverse. Before we do this, and by the way, so we can immediately write the respective matrix 1, 0, 0, 2. And now, what is the determinant of P? The determinant of P is minus 1. So here, we're going to have minus 1 times, we have here 1 and 5, and minus 3, minus 2. So this minus 1 goes inside, so this becomes like this. This is plus, plus, minus, minus, okay? So apparently, we ended up finding the P, D, and P inverse. So this is all that we need, okay? We don't need anything else. So then, let's try, we want to find the xt. So allow me to take this out for a moment, because we calculated those correctly. So we're looking now for what is a to the power t. A to the power t, based on what we wrote before, this is equal to p, d to the power t, p inverse. P is equal to 5 to 3, 1. And d to the power t, it is 1, 0, 0, 2 to the power t, times minus 1, 3, 2, minus 5. Then this would be equal to, so the multiplication of these two terms, this would be equal to 5, 3, this row times the first column. What do we get? This is 5. And then this is equal to 2. Then we have 3 times 2 to the power t. And then this row times this column, we get 2 to the power t. 2 to the power t. And we multiply this one with minus 1 to 3, minus 5. And this is equal, we should get another matrix, which is 2 by 2. In this case, we have -5 plus 6 times 2 to the power t. Then we get here 15 minus 15 to the power t minus 15 times 2 to the power t and then we have -2 plus 2 times 2 to the power t, and then 6. What is this? We multiply this row with this column, so we get 6 minus 10, right? 2 to the power t. So this is a to the power t. Then our question is the following: what is x? Wait a second. Yes. What is xt, yt? This is equal to a to the power t times the initial condition times the x0. x0, it was 1, 1. So this 1, 1, this is 2 by 1. So this matrix, which is 2 by 2, we need to add these two together. And here, what we get is that we're going to get the first column plus the second one, okay? So the first column plus the second one, this will be, is it clear why we have these two together? The first column times the second, maybe it's best if we can write the whole thing, -5 plus 6 times 2 to the power t, minus 2 plus 2 times 2 to the power t, 15 minus 15, times 2 to the power t, 6 minus 10 times 2 to the power t. Okay, so finally, we get this number plus this number, we get 10 minus 9 times 2 to the power t. 4 minus 8 times 2 to the power t. Okay, so this is how these two values, the x and y, this is how they will change as a function of time. So if we want to know what is the number x and y at the time frame t equal to 4, so let's check, for example, what is x4, y4, then this will be equal to 10 minus 9 times 2 to the power 4, and 4 minus 8 times 2 to the power 4 again, times 2 to the power 4. This is equal to 2 to the power 4, 4 times 4, 16, 16 times 9, 48 times 3, 144, minus 10, minus 134. I hope this is correct. You can check if it's right or wrong. Then here we have 2 to the power 4. This is 4 times 4, 16. 16 times 2 is 32, 64, 128 minus 4, minus 124. Okay, so this is the number that we find for x after 4 different times frames. So let's see it again. We started with 1, 1, okay, and then we end up much later with minus 134, minus 134, and minus 124, minus 1, 2, 4.
Does this mean the rabbits have gone extinct?
No, this just means that this is not a real equation for biological systems, because biological systems don't go at negative numbers, but this could be like the coordinate in XY space. This is not the best formulation, okay? So we're just coming up with negative numbers. If you want to count something, it doesn't make sense, of course. But this might be defined as a change. So the rate of change, this is, so what this would work perfectly is if this is not the absolute value for the for some biological systems, but if this was the rate of change. So in blue, I can write the following. I can say that dx over dt, or we can say that dy over dt. So these are a couple of differential equations which are coupled, which we are going to do together, most probably next session. Okay. So this might mean that if you have rabbits and foxes, because of they might be competing with respect to each other, after 4 different time scales, the rabbits might be decreasing 134 rabbits per hour or per year, and the foxes might be decreasing 124 foxes per year. So it might be decreasing if we have such a system. And we are adding this part just to make sense if these were biological samples or animals. Okay? But if we get negative numbers, what would be acceptable is that we might have the evolution of a point in Cartesian coordinate system, which we start somewhere here at 1, 1, and it looks like this is going to move very fast into the negative numbers, but we don't know where this is going to go. Let's see, minus 134, minus 124. Yes, it looks like it has a slope less than 1, so it goes somewhere here. So each time we're going negative and more negative. And this one, it is obvious in here. So, okay. Okay, so we started with 1, 1. We ended up with minus 134 and minus 124. And please check these numbers. I might have done something wrong, so just double check, okay? And then what we can also check is the following. So we found the solution of this problem, okay? Everybody's happy with it. And we might want to see what was the number of what was x and y in the new basis, okay? So in order to do that, we know that we come this way with p, and we go backwards with p inverse. So do you have any idea what is this vector? The 0 vector. So we are looking for this, the corresponding vector in the new basis. So this is the standard basis, okay? So what is this? And we can also ask the following question.
P minus 1 times 1, 1.
Say it again, P minus, say it again.
P minus 1 times 1, 1. Like the inverse of P times 1, 1.
You mean this?
No, not A, P.
P inverse, okay, yeah, that's correct. You are right, that's what we should get, okay? So the initial condition in the new basis, it should be equal, as you said, P minus, because 1, 1. So this is equal to minus 1, 2, 3, minus 5 times 1, 1. And this is equal to, what is this? 2, and then 2 minus 5 minus 3. Okay, we found it. This is 2 minus 3. This is 2 minus 3. And then what we can also try to find is the following. If we have, in the standard basis, if we have that xt is equal to at times x0, we can also assume that we have a vector u, which is equal to d to the power t times u0. Okay? So the evolution of these points, maybe the best way to think about this is the evolution in xy space. If we have 2 points, let's assume that we have some points which change as a function of time in xy Cartesian coordinate system, but they might be looking a little more different if we see those in this reference frame, 5, 2, 3, 1. Okay? So we found 2 minus 3. So how can we find, let's try to find what is ut. Then ut, which let's denote as ut vt, so let's assume this is not a single vector, but it's composed of 2 entries. This will be equal to t to the power t. T is 1, to the power t is 1, 0, 0, 2 to the power t, times the initial state, which is 2 minus 3. Okay? So then this is equal to, what is this equal? This is, what is ut? Just 2, okay? It's a constant number. Let me see, yeah, this is just, that's it. What about vt?
Minus 3 times 2 to the power of t.
That is correct, okay? So what we find here, we notice that, yeah, this is the solution. So we have ut is equal to 2 and vt is equal to this number. So then, so this has a relatively simpler solution because it's keeping one component the same. It's not changing, okay? And let's look for a moment what is ut, what is u4 and v4. So if we substitute the values here, we get u4, it will always be equal to 2. And the v4, it's equal to 2 to the power 4, it's 16 times 3.
Minus 13.
Minus what?
No, minus 20. 48, yes.
Minus 48, okay. So we get minus 48. So here we get 2 minus 48. This is 2 minus 48, okay? Now, how did we find this value? Normally, we had here 1, 1. From this 1, 1, in the standard basis, we found that in the new domain, we get this, okay? Then, from here, we used the initial condition in this basis to find this new value, okay, which is 2 minus 48. But now, is there any other way to find these numbers? What we can do is that we can find another relationship between this 2 minus 48 and this number here. Would you agree? So I don't know where shall I bring this one, so let's come here this way, and here. Let's project this one from here to this other side. How does it come through? So if we multiply p with 2 minus 48, what should we get?
We should get minus 134 minus 124.
Exactly. Let's see if we get that. We should get it. So it's like we're trying to confirm what we are saying for a long time. So here we have 5, 2, and the 3, 1. The number is 2 minus 48. And this is equal to. So here we have 5, this is equal to 5 times 2, this is 10. 10 minus 48 times 3. What is 48 times 3? This is 128. 20, 24, 134, right? We get minus 134. And then we have also 2 times 2. Wait a second, this is 5, 2, 3, 1. So here we get 2 times 2 is 4. Minus 48, we get minus 44. So we did not get the same numbers.
Professor, I think there's a mistake at the matrix where we calculated a times a in power t times 1, 1.
Yes.
The cell 4, there's 6 minus 10 times 2 to the power t. I think it would be minus 5 times 2 times the power t.
Here?
Yes.
You mean we need to correct this?
Yes, I think the 10 should be 5.
Let's see this one. So
Yes, that should be a 5. That's minus 5 times 2. That is correct.
this is minus 5?
Shikoni resh më sipër. Po, një çik më majtas. Në mund punojmë matricën këtu për sa të shumë puni. 2 herë 3 dhe 2 herë minus 5.
Minus 5. Oh, this is minus 5. Okay. This is minus 5.
Ka drejtë.
So this is, oh, okay, okay. So this is 6 minus 5 times 2 to the power t. Then let's correct a few things. Then here, we're going to get, wait a second. So then, this will be, this is 4, this is correct. 2 minus 5, this is minus 3 then, right? Right, because we add up this number times 1 plus this number times 1, so this is 4 minus 3 times 10. Okay, this is correct. Then so we can fix this. Then this is also minus 3. So then we get 4, 2 to the power 4, 16, 4 minus 48. This is, okay, so this is minus 44 then. So if this is minus 44, we made a mistake here, we can correct it here, minus 44. This is 174. Okay, so it looks like we are better now, right? So we confirmed through 2 different, so we got equal this answer here, okay, and this answer here. Now, the question is the following. Which one of the methods was shorter? So, if we used, let's assume that our fundamental question was this: find u4, sorry, find x4, which means that find x, vector x, after 4 stages. x4 is equal to what? If this is the question, let's see how much space did we need here to solve the problem. All we needed to do was that we needed to know this. So we found this u0, okay, which is the initial state here. We multiplied it with d to the power t, and we got this. So, and then this is equal to this. Then this number 2 minus 48, we projected it back here. So it looks like with these 3 elegant equations, and it was not that difficult, with all, even you might even forget this. So in 1, 2, 3 steps, we found the answer of what is x after 4 stages. How did we do it? We were given the initial state here, 1, 1. We found the initial condition here. We generated in time in this elegant domain, or more elegant domain, and we got the answer. The other way around, so this was one solution, and it looks good to maybe to most of the viewers, or we will do this, and it looks like we have some considerable amount of matrix calculations. Yeah. So for a matrix system, which is 2 by 2, the ratio is like you need 1 meter square here, you need 2 meters square here, okay? You need more paper in an exam. So this looks like a more elegant way to solve the problem. Okay, this is an interesting approach, but I want to have a look again, to have a look at the geometric representation. So let's see. I'm afraid I cannot draw this one very to scale. But let's assume this is the x, and the y. And here, the original coordinate system is x and y. So this basis is 1, 0, 0, 1, but the new basis is 5, 2, 3, 1. Now, 5, 2, this is 1, 2, 3, 4, 5. And 2 is this vector. So this is one of the basis vectors in the new domain. And the other vector is 3, 1. 3, 1 is 1, 2, 3, 1 is here. The blue, it does not have a very high contrast with respect to the black. Okay, so this is the new basis. And then the initial condition in this new basis is equal to what? This is equal to 2 minus 3. 2 is this 5, 2, we have 5 units like this. So this will go up to, this is 5. Now, if I try to draw something to scale, I'm going to get something like this. I'll try to do my best, and I promise. So this is 10, because 2 times 5, 2 is equal to, so the initial point is 2 times 5, 2, minus 3 times the other axis, which is 3, 1. Allow me just 1 second. Hello? Okay. Peut-être. Oh, sorry, il y a une élection pour vous sorry. Okay, so we have here 5, 2, so we're talking about some vector which is going to extend all this way. Then we subtract 3 units of these. So in the end, actually, we know that we're going to end up in here, but I cannot draw this one to a perfect way. But what I want to observe is this. How is it possible that this new vector in the new coordinate system, this will always be along the first domain? We get 2 units of these, minus, so 2 units of the first of the u. It's like we are starting from here, and we are subtracting each time this much. Okay, so the u is 2 units along this, and then we have to subtract. Okay, no, now I can figure this out. So it looks like from this point here, we have to move how many units? This is minus, so after 1 second, when t is equal to 1, we're going to get minus 6. So minus 6 is going to be minus 6 of this vector. Okay, so this is 3, 1. This is going to be minus 6 times 3, 1. So this is going to be minus 18. Minus 6. So this is a very, so it's going to be a huge, so after a single step, we're going to have 2 units of this vector minus 6 times this one. But now I cannot really draw this one to scale on the board. Probably it's better if we draw this one on a computer, on a software, okay? But I hope that this is clear. Do you have any question for what we did so far? Okay, if there is no question, we can have a short break.